Welcome to Quick Course Digest. Today, we are tackling Calculus 1. And look, before you get scared off by all the formulas and symbols, let's just push those aside for a minute. Because at its heart, calculus is really just a story. It's an amazing story about how we finally solved two of the oldest, most fundamental questions in all of math. How do things change in a single fleeting instant? And how do all of those tiny, tiny changes add up to become something big? So here's how we're going to break it down. First, we'll dive into that problem of change. Then we'll build up our special toolkit for dealing with it. After that, we're going to tackle the second big question, the problem of accumulation. And this is the best part. We'll discover the incredible fundamental bridge that connects these two seemingly separate ideas. And finally, we'll see why this whole thing matters so much in our world today. All right, let's jump in. All right, section 1, the problem of change. You know, for centuries, we've known how to figure out average speed. That's pretty simple, right? It's just your total distance divided by your total time. But there was a much trickier question that stumped people for ages. How fast is a car moving right now? I mean, think about it. You're in a car, you look down at the speedometer, and it reads 60 miles per hour. That's not your average speed for the last 10 minutes. No, it's your speed in that one specific instant. But how is that even possible? An instant lasts for 0 seconds, so how can you measure a speed over 0 time? That was the puzzle. Okay, let's visualize this because it makes a huge difference. Average speed, that's easy to see on a graph. You just pick 2 points in time, draw a straight line between them, that's called a secant line, and find its slope. Done. But instantaneous speed, that's different. That's the slope of a line that just perfectly kisses the curve at one single point, a tangent line. And that's the problem. How in the world do you find the slope of a line when you only have 1 point to work with? And the solution, it's just brilliant. It's called the derivative. So what is it? Think of the derivative as a new magical function. You feed it your original function, like the one tracking the car's position, and it spits out the exact, precise, instantaneous rate of change, that slope of the tangent line, for any point you want. It's the perfect tool. It's the speedometer, but for any kind of change. So now we get to building the derivative toolkit. I mean, it's great that we have this concept, but drawing a graph and trying to eyeball the slope of a tangent line every single time? No way, that's way too slow and inaccurate. So mathematicians got to work, and they developed a set of incredibly powerful shortcuts, a whole toolkit of rules that lets us find the derivative for pretty much any function you can think of without ever drawing a thing. And here are the essentials in that toolkit. You've got the power rule, which is your go-to for anything with an exponent, like x squared. Then you have the product and quotient rules for when you're multiplying or dividing functions. And then there's the chain rule. Honestly, the chain rule is the real superstar here. It's what lets us handle functions that are nested inside of other functions, which happens all the time. You master these, and you can take apart almost any complex function piece by piece. And check out this perfect real-world example of how this works. We call these higher-order derivatives. If you have a function that tells you an object's position over time, okay? Take the derivative once, and bam, you get its velocity. That's how fast its position is changing. But why stop there? Take the derivative of the velocity function, and you get acceleration. That's how fast the velocity is changing. It's this beautiful, logical chain that perfectly describes motion. Okay, let's totally switch gears now. We're moving on to the second great problem of calculus, the problem of accumulation. So forget about instantaneous change for a moment. Now we're asking the opposite question. How do things add up over time? And what that looks like visually is trying to find the exact area of a weird curvy shape. So here's a real-world puzzle for you. How much water has flowed from this pipe over 5 hours? Now, if the flow rate was constant, that's easy. But what if the rate is changing all the time? Maybe it starts as a trickle, then gushes, then slows down again. You can't just multiply rate by time anymore, because the rate isn't a single number. It's constantly in flux. So how do you find the total? The strategy for this is actually pretty clever. We take that weird curvy area that we can't measure, and we approximate it with something we can measure, simple rectangles. The idea is to just divide the whole area under the curve into a bunch of skinny rectangles. We know how to find the area of a rectangle, right? So we just calculate the area of every single one and add them all up. It's not perfect, but you can see that the more rectangles we use, the thinner we slice them, the closer we get to the real answer. So what's the perfect solution? It's called the integral. The integral basically takes that rectangle idea and pushes it to the absolute limit. It asks, what if we could use an infinite number of rectangles, each one infinitesimally thin? Well, if you could do that, your approximation would become exact. And that's what the integral does. It gives us the precise total accumulation under the curve, the exact amount of water that came out of that pipe. And now we arrive at the fundamental bridge. Okay, so for hundreds of years, these two problems, finding slopes and finding areas, were seen as completely separate things. I mean, they lived in different mathematical universes. One was about an instant, the other was about an interval. Nobody thought they had anything to do with each other. Until there was one of the greatest aha moments in human history. A connection was found. I mean, just look at them side by side. Are they two sides of the same coin? On the one hand, you have differentiation, finding the slope, the instantaneous rate of change. On the other hand, you have integration, finding the area, the total accumulation. One is about zooming in to a single point. The other is about summing everything up. They really do seem completely unrelated. Or are they? This is it. This is the whole ballgame, the fundamental theorem of calculus. And what it says is so simple it's almost hard to believe. It says that the processes of differentiation and integration are simply inverses of each other. They're opposites. They undo one another. And this was the aha moment. They are opposite operations. It's just like how subtraction undoes addition or how division undoes multiplication. Finding the area under a curve, that's integration, can be completely undone by finding the slope of that area function. That's differentiation. You end up right back where you started. And this was a game changer. It meant that the super hard problem of adding up infinite rectangles could be solved by doing the opposite of finding a derivative, which was way, way easier. So why is this one of the most important ideas ever? Because calculus in our world isn't just some abstract math puzzle. It is, and I mean this quite literally, the language of science, engineering, and economics. It's the code that our modern world is written in. Just think about all the places it shows up. In physics, it's describing the motion of planets and rockets. In business, it's used to find the exact point of maximum profit. Engineering, you can't design a stable bridge or an aerodynamic car without it. Even in medicine, it's used to model how drugs work in our bodies. Oh, and the incredible 3D graphics in movies and video games? Yep, that's all calculus too. It is the engine running pretty much everything behind the scenes. So when you strip it all away, this entire massive, world-changing field of calculus I really just boils down to two core ideas. The derivative, how fast is something changing right now? And the integral, how much has it all added up? That's it, change and accumulation. So now that you get the core ideas, here's a final question for you. Where else in your world do you see these patterns of change and accumulation? I mean, really think about it. Once you start looking for this stuff, rates of change and things adding up over time, you'll start to realize it's literally everywhere.